Today I'm going to explain about the concept behind the helol-Tunnel. So it's a research project that demonstrates how hidden data can be transmitted through TLS handshake packets. So we will walk through the idea step by step so that even if you are not familiar with TLS internal, you can still understand how the mechanism works. So if you capture the traffic in Wireshark, you can observe the relevant data directly in the TLS handshake. You can just apply a filter and you can isolate client hello messages. And when you expand the cipher suit section in each client hello, you will be able to see the exact ordering of the cipher list. So in this video, we are going to see how that ordering is where the hidden data is embedded. So first, let's briefly talk about what happens when a browser connects to a secure website using HTTPS. So before encrypted communication begins, the client, for example, your browser, sends a message called client hello. So this message contains information about the cryptographic options the client supports. So one of the messages is a list of cipher suits. So as you can see, these are the encryption algorithm the client is capable of using. So for example, a client hello message might include a list like this. Important detail here is that TLS server generally do not require these cipher suits to appear in a specific order. So the server simply looks at the list and chooses one cipher suit that it also supports. So because of this, the order of the item in the list does not affect whether the connection succeeds. So the hello-Tunnel takes advantage of that here, that instead of sending the cipher suits in a normal fixed order every time, the program changes the order deliberately. So each different order represents a number. So that number represents part of a hidden message. Let's understand with a simple example. Like suppose we have three items in a list that is A, B, and C. So these items can be arranged in different orders, and like ABC, BCA, and ACB or CBA. So there are six possible arrangements here. So because of there are six possibilities, we can assign a number to each arrangement. For instance, ABC will be 0, ACB will be 1, and BAC will be 2, and so on till 5. So now imagine a sender wants to transmit the number 3 here, and instead of sending the number directly, the sender construct a client hello packet where the cipher list appear as BCA. So when the receiver sees that order, it compares it with the predefined list and determines that the order correspond to the value 3. At this point, you might wonder, how do both sides know that BCA equals 3? So both the sender and receiver start with the same base list of item and use the same deterministic algorithm that converts a number to a specific permutation of that list. So the same input always produce the same output here. So if both sides agree on the same list and same permutation mapping logic, they will interrupt the ordering in exactly the same way. Let's connect directly into the code, that how the code will show that how it works. So the program defines 5 fixed TLS cipher suits here, giving 5 factorial means 120 possible permutations here. So it can generate all permutation of those 5 position and uses each permutation position as a numeric value from 0 to 119. As we are using 0 index, so it will be till 119 only. So as we can see, the script then takes a message here, for example hello secret, and it goes through the message one character at a time. So it converts each character into its ASCII value, keep that value within the range till 119 range using modulo of 1120, and maps it directly to one of the stored permutations. So here that permutation is then used to reorder the base cipher suit list. So if we run this code, we can clearly see this happening in the console. For each character, the script prints the character, its ASCII value, and the computed number, and the order, and the permutation that is being used, and the resulting ciphering order you can see. So now you can tell literally uh, that how a simple letter turns into a number and how that number turns into a specific cipher ordering. Now, now the reordered cipher list is then inserted into a TLS client hello object using Scapy here. So the our program build a minimal but a valid looking handshake packet around it. So structurally it is completely a normal TLS client hello message. The only thing that changes from packet to packet is the ordering of the cipher suits. Each packet here becomes one client hello packet, So after generating all the packets, the script simulates the receiver side. It reads each packet, extracts the TLS client hello, look at the cipher ordering and determine which permutation it matches, and recovers the numeric value. That number is then converted back to into a character, and as the script runs, you can see the decoded value printed in the console, followed by the reconstructed message at the end here. So what makes this technique interesting is that TLS structure itself remains valid, the cipher suits are legitimate, and the handshake format follows protocol rules. Only the ordering of element in a flexible list is being used as a signaling channel here. So where could something like this appear in practice? A covert channel like this would most likely originate from a compromised endpoint. For example, malware on a infected workstation could generate outbound TLS connection to a remote server and encode a small control signal by permitting the cipher list. On the network, this traffic would still appear as normal HTTPS handshake. It is also important to understand what modern TLS features do and do not prevent. So TLS 1.3 simplified parts of the handshake but still allows ordered list as the cipher suits and extension. Ordering flexibility remains here. So encrypted client hello or ECH is a TLS 1.3 extension that encrypts sensitive metadata and inside the client hello, especially SNI and certain extension. It does improve privacy by protecting the information, but ECH does not prevent permutation based signaling in fields that remain visible in outer client hello and does not enforce a fixed ordering of cipher suits. So providers such as Cloudflare have supported and deployed ECH to enhance internet privacy at a scale, but this reduces exposure at metadata like SNI, but it does not eliminate the flexibility in ordered handshake fields. So in conclusion, helol-Tunnel demonstrate that protocol flexibility can create covert communication surfaces by encoding numbers into permutation of cipher suits inside TLS hello messages, client hello messages, and hidden information can be transmitted without violating the protocol rules. We have also observed the cipher ordering directly in Wireshark using a client hello filter, and we can see the full encoding and decoding processes in the console output when the script ran. And although TLS 1.3 and ECH improve privacy for sensitive metadata, but they do not inherently remove the ordering based on signaling surfaces.